Okay, good morning, everyone. For today, I have a couple different things. These are here in the same GitHub repository as always. Today we're on session 6, and the first thing I'm going to do is this filtering. And this is all about filtering. I already introduced some notions of filtering last week, but I wanted to give a more detailed explanation of what aliasing is, when does it happen, how do we do filtering to prevent aliasing, and essentially how these three concepts, decimation, aliasing, and filtering, are related. The goal here is basically to crop out signals in the spectrum. So we're already familiar with the FM broadcast spectrum, for example, or any other kind of spectrum where there are multiple signals, and we might capture all of them with RSDR, but perhaps we are interested in just processing one of them. Again, the example is an FM receiver. We only want to tune to one single station at a time. So we need to crop out that signal and remove all the rest. And for that, we use filtering. And also, we take advantage of the fact that we are removing spectrum to perform decimation. That essentially means reducing the number of IQ samples per second that we need to deal with. And that is good for compute because it's less numbers that our computer needs to work with. So things are faster, or they use less CPU, or however you want to view this. So filtering, it is essential. And then the second part is an FM receiver. So a broadcast FM receiver. We saw that on the first week using GQRX. Now I'm going to show you how to build that in GNU Radio. What are the building blocks of this thing? And you will see that there are multiple filters there. So I think this is a nice application of filtering. It basically shows that many kinds of radio receivers, whether analog or digital, have filtering as one of the basic building blocks. So let's get started with the filtering thing. I'm going to open GNU Radio Companion, and this I'm going to make from scratch. I actually have it here, but I'll begin from scratch. So I'm going to set the sample rate to 1 megasamples per second. That's 1 megahertz spectrum. It isn't critical. We could use anything. This is going to be a simulation, but I like just 1 megahertz. It's not too large, not too small. And then I'm just going to generate a signal. So a constant, a CW carrier, basically a signal of constant amplitude and frequency in Gaussian white noise, as we have done on other occasions. So we know we can do that with the signal source, and maybe this is too large. So signal source and noise source, we can add them. And then we have our signal in Gaussian noise. I'm going to make the amplitude of this thing a little smaller, for example, 0.1. I'm also going to add an entry for the signal, for the frequency. So let's call it frequency. It needs to be float. And let's say this is going to start at, I don't know, maybe 50 kilohertz. So I want to put in here frequency. And then I need a throttle block because this is a simulation. So otherwise, it's going to run as fast as my computer allows, which is way too fast. And then a frequency sink to show the spectrum. So this is nothing new. We have been doing things like this, many of the tutorials. Maybe I want to put some averaging in here. Yeah, like medium averaging. I will just edit this and make it permanent. So averaging medium. And so we can see our signal. Nothing too surprising. We have the white noise floor. We can see the signal. And then the frequency is 50 kilohertz, as I indicated. And I can change it here. For example, if I make this, I don't know, 150, it will jump. It jumps instantaneously, but because I have an average on the FFT display, we see like it disappearing appearing at a different frequency, like if I do this. So, okay, all of this is working. Maybe I want to make this from -60 to, I don't know, -10 or something like that to have a more reasonable range. You can change the range of these things in the properties. And now the first thing is, well, let's say that we are interested in receiving this CW signal for further processing. Further processing could mean whatever. In the example we are going to do on the second part of today, it's going to be an FM station. So whatever will be essentially converting that FM signal to audio we can listen. In this case, it's like an abstract example, so just bear with me. We want to tune to the signal for whatever. And the usual way of tuning to a signal, we have already seen that in the past, is to shift the signal to 0 hertz. So we call that baseband. Essentially, the signal is here, or it might be anywhere. We want to place it in the middle. We want to place it at 0 hertz, right here, because then that will make us, it will simplify our life when we want to operate with the signal. So if we want to do that, we already know how to do it. We have already seen that we can have a signal source which plays the role of the local oscillator. And I'm going to call this tune frequency because it is the frequency to which we are tuning our receiver. So maybe, I don't know, maybe let's make this 30 or whatever. And we multiply conjugate. If I do this, and I, of course, need to set here the frequency to tune frequency, what's going to happen is I have this at 50 kilohertz. I have this one at 30 kilohertz. I'm doing the multiply conjugate operation. So with the thing I will get here is a CW carrier, a tone at a frequency which is the difference of the input frequency. So 50 minus 30 equals 20. And then I'm just doing this like so for the sake of the example. In our radio, if this was like a car radio receiver, we would move our knob, if it has a knob, or press buttons to change the frequency so that these 30 kilohertz matches the 50 kilohertz that we want to receive. And then in that situation, it will be in the middle of the spectrum. So let's put names here, input signal, and then signal after mixing. This mixing is the usual name for the operation, which consists in multiplying by a local oscillator to shift things in frequency. So is this what we expected? Yes, it is somewhat confusing because input signal is on the bottom of the plot. I actually want it on the top. And I'm going to show you how to rearrange these plots because I think I haven't introduced this theater yet. But input signal is here, so 50 kilohertz. And then 50 minus 30 equals 20. So we get this as 20. So far, I guess no surprises. Any questions? Okay, so if we have plots in the GUI, GNU Radio will order them in whatever way, but we can influence that order to essentially order things in the way we want. And there is a thing which is called GUI hint, which is here. And I think there is a reasonable explanation in the wiki. Let me just Google this. So if you Google for GUI hint, GNU Radio, you can see essentially these are like coordinates of a matrix. For example, if we want to have like 4 columns and 3 rows, we could label things at 0, 0, 0, 1, 0, 2, etc., etc. But then it's also possible to have different sizes in the plots. In this example, all 6 or 12, all the 12 things are the same size. In this one, we have, I don't know how many, 5 different plots, but they have different sizes. And the way to have different sizes is to add these two additional numbers, which indicate how many rows and columns the thing is taking up. So for example, this waveform selector is at coordinate 0, 0, but it's actually taking up 2 rows and 1 column. So that's what it makes this twice as tall as this one, which is only taking 1 row and 1 column, 1 row and 1 column. So this is basically how it works. Basically, row and column index, and then how many rows, how many columns needs these to occupy. And these two, the row span and column span, are optional. If you omit them, it's implicitly meant to be 1. So for example, this one, we could say just 0, 1 instead of 1, 1. So that's how to set the GUI hint. And very simple here, I'm going to do 0, 0. So this will be in the top left corner, and then 0, 1 will be in the top right corner. And so far I only have 2 plots, but I will keep adding a few other plots to this thing. So now we can see this more clearly. We can see the signal begins at 50 and ends up at 20 kilohertz. Maybe I actually want to do like, I don't know, 350 and then 330 to make it clear that we are tuning to something which is, it might be here, but after tuning, we place it close to the middle. Okay. So now the thing is, our signal actually has a bandwidth of 0. We can zoom in, and that's the only thing that we care about, this signal. So we could say, why do we need to have this spectrum, which is 1 megahertz, if the only thing we care about is just this little signal, which is in the middle? We could reduce our spectrum. We could basically crop things. Basically what I'm doing here with the zoom. So we could reduce the amount of spectrum that we are processing. Then how to do that? A naive idea would be to say, okay, so the sample rate sets how wide my spectrum is. Essentially, we have 1 million samples per second. And that's what gives me 1 megahertz of spectrum, from minus 500 kilohertz to plus 500 kilohertz. What about just throwing samples away? I can, for example, if I want to reduce the spectrum to 1/10, so that's to 800 kilohertz, then I can take 1 sample in every 10, and that means first sample I take it, then I drop 9 samples, next sample I take it, I drop 9 samples, and so on and so forth. So that is the naive idea. We're going to do that. We are going to see what goes wrong in that case, and then we will see how to fix it. Already you can suspect that this idea about throwing away samples is not going to be very good, because we are throwing away information. If we have 10 samples to begin with, those are numbers which contain some data about the signal. If we only take one of them and throw the other 9, somehow we are throwing away information. So that lack of information will need to show up somehow in what happens. But nevertheless, let's try that to see exactly what happens. So in GNU Radio, there are multiple ways of doing that operation, essentially taking 1 sample in every 10. The simplest way to do it is with this keep 1 in n block. And this is self-explanatory. N is a parameter, so I'm going to add a variable, which is going to be called decimation. And then I can set my variable right here, decimation, and I'm going to set it to 10. So keep 1 in n becomes keep 1 in 10, and this will keep the first sample in every block of 10 and discard the remaining 9. So that's the operation I want to do. I already mentioned that it's problematic, but we want to do it nevertheless to see why it causes problems. So I'm going to show this. This is going to be signal after decimation. This is called decimation. So removing samples in digital signal processing is called decimation, which technically means taking 1 in every 10. Decimation has the Latin root for 10. But these days we use decimation for any ratio. We can say decimate by 3 if we are taking 1 in every 3 samples, decimate by 100, decimate by 7. Any integer number you think of, we can speak about decimate by. Another synonym is downsample. So if you ever hear about downsample by a factor of 15, that's the same as decimating by 15, and that's the same as keeping 1 in every 15 samples. So, okay, this is signal after decimation, but one thing we need to be aware of is that the bandwidth is now reduced by this decimation. Otherwise, GNU Radio doesn't know. GNU Radio just knows that there are complex samples arriving here, but it doesn't know anything about the sample rate they have. It doesn't know anything about time. There is no absolute concept of time in GNU Radio. It's just you have a stream of numbers and they get plotted. So we need to tell it. And then we are getting an error because since I have copied and pasted this block, the GUI hint is also copied and pasted. And GNU Radio is complaining that there is another block in the same location. So that doesn't make sense. We cannot have two plots in the same location. We need to put this on the second row on the left, for example. So this is the signal after decimation. Let's see what happens. So, okay, things look reasonable at first glance. We know the signal after mixing is at 20 kilohertz. And here we see our signal at 20 kilohertz. It's a sound wave. It looks fine. The spectrum, you can notice it's now from minus 50 kilohertz to plus 50 kilohertz. So it's just the central plus minus 50 kilohertz. That's what we wanted. So far things look good. Let's see where problems can appear. Let me begin changing the frequency of this signal. So let's try to make this, I don't know, the frequency is here. So let's make it 360, for example. And then it comes here. So that looks fine. That's what we expect. I'm going to increment it in steps of 10. Then 370, it comes to 40. Then 380. It's here as we would expect because here it's at plus 50 kilohertz. So now we see the signal at plus 50 kilohertz here. You might also notice that it's at minus 50 kilohertz. And the reason for this is in digital sampling, you should think about the spectrum as being glued by the edges. So this thing is glued to this. You should think about the spectrum as laid out into a circle rather than flat, as it's shown here, because essentially there's no way to distinguish this frequency, which is the plus the sample rate divided by 2, from this other frequency, which is minus the sample rate divided by 2. So, okay, maybe this is expected because, I mean, we have the signal like right at the edge of the spectrum we can handle. So, okay, but then what happens if I increase by 10 kilohertz more? Should it go away? Well, it goes away in here, but now the signal is there. And that is clearly wrong because we have the signal here at 60 kilohertz. 60 kilohertz is like over here outside of the plot. And nevertheless, we see this at minus 40 kilohertz. So what is going on here? This is known as aliasing. I have already given you a clue by saying that this end of the spectrum, you should think about it as being glued to the left end of the spectrum. So if we push things too far and essentially exit in this direction, we appear again on the left. So that's one way of explaining this effect. Another way of explaining this effect is to say that because 60 kilohertz cannot be represented in the output because the output can only go between minus 50 and plus 50, we will take, or we will see whatever frequency is equal to 60 kilohertz plus minus a multiple of the sample rate. And if you do the math, 60 kilohertz minus 100 kilohertz, which is the sample rate here, gives us minus 40 kilohertz. So that's another way of understanding why we are seeing this at minus 40 kilohertz. And another way you can think about this effect is these videos, for example, that people post online of something like a propeller, which is being imaged with a phone or a video camera. And what happens there is that the propeller is spinning too fast for the camera to be able to capture it. Maybe the camera does only 30 frames per second. And then what happens if the propeller makes one full rotation and just a bit more every frame? You will not see the full rotation. You will see just a bit more. So every frame you see that the propeller has rotated just a bit more, just a bit more. You don't see that it's actually rotating one full rotation in addition to just a bit more. And then when you look at the video, it appears that the propeller is rotating very slowly, almost frozen. So that's another aliasing phenomenon. It essentially happens when we have a frequency that we cannot represent with the sample rate we have. Because I'm mentioning these videos of propellers or similar things, you might have also seen these videos where the propeller is like wobbly. That's the rolling shutter effect. It's another effect which is only slightly related to aliasing. What happens there is that the camera on the cell phone is not able to capture the image instantaneously, so it basically scans the image, and so we see the propeller at different times in different parts of the image. uh, but if you have seen these, I don't know, with a video camera, like a proper video camera, it it can seem that the propeller is almost still or even spinning backwards. Think about what would happen if the propeller is making almost one revolution. So one revolution minus a little bit. You would only see this minus a little bit. So this is basically what's happening here. This 60 is basically the same as doing one full rotation and then a 40 kilohertz with negative sign. So we only see the 40 kilohertz with negative sign. Uh, okay, so that's pretty bad. It's unintended because now you can think about the original situation where we had our signal. It was at 20 kilohertz and it appeared here, and that's good. That's what we want. But then if there are other places in the spectrum where we can see something at 20, for example, if I how much do I need to put here? 460 maybe. That was too much. 450. For example, if I have a signal at 450, this one is supposed to be originally at 450. That also ends up here at 20 kilohertz. So now you can imagine the situation. We have our signal of interest here at 350, but there is something else at 450, and the two of them end up in the same place. So that's pretty bad because they are going to interfere. Questions at this point? Also, in this really simple situation where there is only one signal, we are still getting degradation. And the reason for that is, well, the noise that we have here, like besides our signal, comes actually from different parts of the spectrum. So it is the noise that was at 350 kilohertz. Also the noise here at 450. Also the noise at 250. Also the noise at 150. And you see how this goes on. So what happens is basically we are folding 10 copies of the noise floor into the same place. And if the math is right, we would expect all of those copies to combine. And so we would expect the noise power to increase by a factor of 10. And if that is true, and I tell you this is true, we will show that in a second. But if you believe me that this is true, then that is pretty bad, because if we are increasing the noise power by a factor of 10 and our signal is still the same because it's just this single signal, we are decreasing the signal to noise ratio by a factor of 10 or by 10 dBs, which is pretty bad. We are losing sensitivity. This signal is fairly strong. We can see it easily, but if it was a weaker signal, we might miss it altogether in this plot. So let's do some numbers, some very simple numbers to see that we are effectively losing signal to noise ratio. So let's look at any of these two plots. I will return the signal to the original 350 kilohertz. So the noise floor is at about, I don't know, minus 44 dBs. Let's call it that. It's at minus 44 dBs here. It's at minus 44 dBs there. You might notice it's also at minus 44 dBs here. Okay, what's the signal level? It's pretty much minus 29 dBs. It's minus 29 dBs here. It's also minus 29 dBs here because the only operation is shifting the spectrum. Well, it might not be exactly the same because of scalloping losses. So maybe the way that the signal is aligned to the FFT beams is slightly different from this one. And you can actually see the shape is slightly different. This one has a flatter top, but the difference is minor. And that's just an artifact of FFT processing. So here, between these two plots, we are only shifting things in frequency. So it's the same signal to noise ratio. And then this one was at minus 29 dBs. What is this at? This is also at minus 29 dBs. Okay, so we have a small puzzle here. Basically, the numbers are all the same in the three plots. The noise floor is at minus 44. The signal is at minus 29. Yet I'm saying that we should see a degradation of 10 dBs in here. And then why is the reason that we are apparently not seeing this? Like apparently these three plots are all the same. The signal has the same height in all of them compared to the noise floor. Does anyone know the reason?
The question was, they all have the same height, right?
Yeah, why do they all have the same height and apparently the same signal to noise ratio in the FFT plot? But I'm trying to convince you that because we have this aliasing, like we are summing up 10 copies of the noise when we do this decimation, why do we not see this loss in SNR in this plot? Okay, it is a slightly tricky question. The answer is actually in one of the tutorials in previous weeks, or the key to the answer. But I will explain it since it's tricky. The reason for this is the FFT size is the same in all three plots. It's 4,096 points. I have been copying the same parameters on the three plots. So that's the reason why the FFT size is the same. However, the sample rate is not the same. It's 1 megasample per second in these two. It's 100 kilosamples per second in this one. So that means that when we measure the signal to noise ratio here, when we say the noise floor is at minus 44 dBs, the quantity of noise or the bandwidth of noise that corresponds to minus 44 dBs is an FFT bin. And an FFT bin here is 100 kilohertz divided by 4096. So an FFT bin in this plot is 24 hertz. And an FFT bin in this plot or in this plot, because they have an identical sample rate, is, I can write it like this, 244 hertz. So that's what's happening. Basically, the noise power corresponding to 24 hertz in this plot is the same as the noise power corresponding to 244 hertz in this plot. So that's where the signal to noise ratio degradation comes from. If we actually compare the signal power against something which is on absolute terms, like the noise power in 1 hertz, then we will see that the signal to noise ratio is 10 dB lower in this plot. There is another way to show this, which is maybe clearer, which is to use an FFT size which is 10 times smaller in this plot, so that we get the same FFT bin width in all the plots. And I'm going to do that because I want to divide by 10 exactly. I'm going to temporarily set, oh no, this needs the FFT size to be a power of 2. Okay, it will be pretty close. Can I set this to 4? No, it will not let me. That's a bummer. Um, we could do this by hand with by building these plots by hand with an FFT block and a vector sync and everything. So maybe that's an exercise for you because I don't want to spend a lot of time putting that together. It's a silly limitation that this only allows FFT sizes which are a power of 2. They are more efficient to compute with the computer, but any FFT size is possible to compute. So yeah, I don't know why
Could you
this.
decimate by 8 instead of 10?
Sorry.
Could you decimate by 8 instead of 10?
Yeah, that's a good point. I can change my decimation and then divide by 8 here. So we can show the effect. Great suggestion. So now what happens? We can even see it. Like in here, it's almost disappearing in the noise. Maybe let's make it somewhat stronger so that we don't lose it. And then let's see. The signal power is minus 20. Let's call it minus 20 dB in this plot. And in this one, it's also minus 19. It should be pretty close to minus 20 because of the way that FFT scaling and decimation works. But yeah. So more or less the same signal power, so to speak, but remember that power is not absolute on any of these scales. And then what happens with the noise floor here is minus 44, the same as before, but here is now minus 35. Probably should measure it like this, and I should get minus 34. So now we see clearly this degradation in the noise floor. Minus 44, minus 34, so it has been degraded by 10 dBs here. Maybe not exactly 10 dBs because now we only have 8. So what's 10 times the logarithm of 8? That's going to be probably 8.5 or something. I need to import NumPy. 9. Okay, yeah, I should know that. So 9 dBs. So, okay, I think this clears things up. Basically, if we do things in this naive way and apply decimation, we have two problems. First of all, we are folding copies of the noise onto the same place, and that degrades the noise floor by however many copies of the noise we are folding on top of each other. And to add to that, also, if there are any other signals that happen to fall on top of the original signal, we also have a problem. Okay, questions? So now that we understand the problem, we can also begin to guess what the solution might be, because the problem, if we look at the signal after mixing, is only the central portion, so only from minus 50 kilohertz to plus 50 kilohertz, will be directly transferred to the output. And the rest, you can think of this as, I don't know, as this is a paper piece and I wrap it around the tube 10 times. So then the other wraps will overlay on top of the central piece. So for example, this from minus 150 to minus 50 also is overlaid here. From plus 50, where is plus 50 here, to plus 150 is also overlaid here. So if we are able to remove all the signals which are outside of what we want to capture on the output, then we don't care that things get overlaid on top of each other because there will be no signals in all of these to begin with. So that's the strategy. Before decimating, very important, before decimating, we want to apply a filter that removes everything that should not appear in the output. So that's everything from, let's say, everything up to minus 50 kilohertz. and then everything from 50 kilohertz upwards. And because the signals we are leaving unmodified are the ones in the center, so those are low frequencies. 0 is as low as a frequency as you can get. Then the filter we need to use is called a low pass filter because it lets signals of low frequency pass through without any modification, and it removes signals of higher frequencies. And higher frequencies in this case will mean for anything which is higher than plus 50 or higher in absolute value, if you wish, than minus 50 kilohertz. So all of these. Okay, so to do that in GNU Radio, I have already mentioned that there is a block called low pass filter. What are the parameters for the low pass filter? There is decimation. I'm going to set it back to 10 because I'm still mentally playing with the from minus 50 kilohertz to plus 50 kilohertz. If we set 8 here, that will change. It will be how much is 1,000 divided by 8, 125, and then if I divide it by 2, so it would be from minus 62.5 to plus 62.5, and I'm surely going to confuse myself with this number, so I prefer to decimate by 10. That makes the numbers simpler to speak them out loud. That's the only reason to decimate by 10 here. So okay, decimation, then gain. Gain is going to scale our output signal. So if I put here 10, then the signal will be multiplied by 10. I can also place a negative number like -1. But more often than not, we just want to leave gain 1, which means that the signals that go through will not be modified in amplitude. If a reason to set the gain here is because the filter is going to do multiplications in any case. So if we also need to adjust the gain for whatever reason, we could integrate that as part of the filter rather than an additional multiplication that is taking up more operations in the CPU. So that's the only reason to have a gain parameter here. Then the sample rate. This is the input sample rate, very important. And then the cutoff frequency. This is where the filter begins removing frequencies. We said this was at 50 kilohertz, and I could fill in 50 kilohertz here, but I usually like to enter the same formula, which is 0.5 times the sample rate divided by decimation. And you will see that in this case, it works out to 50 kilohertz. And this works in general because if we have any sample rate and we are dividing it by any decimation, the output will go from minus a half of that to plus a half of that. So that's always where we want to place the cutoff frequency for the purposes of applying decimation, unless there is another reason to apply a different cutoff frequency. For example, we might apply a smaller cutoff frequency if there is nothing else of interest for us in the rest of the spectrum. I might show an example about that. And then the next parameter is called transition width. So what is that? What happens is an ideal filter would let signals pass without modification up to this cutoff frequency, and then immediately for anything which is a higher frequency than the cutoff frequency, just completely remove it and output zeros for any higher frequency. That is impossible to build. It is mathematically impossible to build such a filter. So the best we can do is to make a smooth transition between the two things we want, which is essentially letting signals pass on the pass band. It's called pass band, and completely removing signals on the stop band. And actually, we cannot completely remove signals. We can only attenuate them by a large factor, for example, 60 dB, 80 dB, 100 dB, whatever is necessary in an application. But we can never completely remove all the signals in a range of frequencies. That is also a mathematical theorem. So we need to do with the kinds of filters that are mathematically possible to build. And that implies a smooth transition, and the transition width sets how wide this transition region is going to be. I will show that in a second. We will see how that looks like. It's the best way to understand it. But just so that you understand, in principle, we want to make this transition width as narrower as possible, because then the filter will be as closer to ideal as possible. But there is a downside to it, which is that these filters, they are called FIR filters, which means finite impulse response. They are essentially a list of numbers. And then the CPU needs to go and multiply each sample by each of the numbers. So if the list is longer, that is, if the filter has more coefficients, then the computer needs to do more operations. So in theory, when we can set the transition width as narrow as we want to, but at some point the filter length will be just unpractical and the computer will not be able to run this in real time. So we want to set this to something quite reasonable. And to begin with, I'm going to set it to 20% of the output sample rate. I usually set it like this. It's easy to remember. So this is 0.5 always, and this is, I don't know, 0.2, 0.1, 0.05. It depends on how good you want the filter to be. So for the sake of the demonstration, I'm going to start at 0.2, and then I'm going to make it narrower. So very important, this needs to happen before decimation. And then because we are before decimation, I'm actually going to put this on the same plot. I'm going to add another input. In this way, it will be easier to see what is the filter doing. So then what's happening? Have I done something wrong? Oh, yes. Okay. For the sake of the example, I want to begin with decimation 1, just to show what the filter is doing. So this in red is the output of my filter. We can see that between more or less minus 50 kilohertz and plus 50 kilohertz, the signals pass unmodified. So you might notice the noise floor is the same, the signal is the same. But then as we go away from that region, signals are heavily attenuated. I can do an auto scale. And you can see essentially the two things I was mentioning. First of all, there is this transition region where the filter is decreasing in output power smoothly. And the width of this is 20 kilohertz, or sorry, whatever this number is. Yeah, it's actually 20 kilohertz. So the width of this is 20 kilohertz. And then this is the stop band. Ideally, we would want this to be at minus infinity, which means attenuating everything completely. It's only a minus 120, but if you compare with this, the attenuation here is, I don't know, 90 decibels, which is pretty high. If you have a signal which remains after being attenuated by 90 decibels, it's because that signal was massive to begin with. So these are the characteristics of any filter which is which can be constructed in practice. Let's change number here to see the effect of the transition width. For example, let me put it 0.05. And then you can see this is much sharper, but the computer is having to do more work. You might even notice, I don't know if it's easy to see, these are like my CPU usage counters, and you can see one of the CPUs is, I don't know, like 50%, maybe 60%. And then if I set this at 0.2, I don't know if this will be a good demo. Okay, this is almost at the same level, maybe not. I promise you, if we make a proper measurement of how much CPU usage we are doing on each of the two cases, this case with a larger transition width should be less CPU usage. But maybe there are other things which are taking more CPU, I don't know, like plotting or generating noise. Generating noise is probably going to take more CPU than filtering because it needs random number generation. For the sake of demonstration, let's also do 40%. This is too much. No one would use this in practical applications. because you can see already that this is minus 50. This is like already too much attenuation because the skirt is supposed to be pretty wide. So that's too much. No one really uses that. But 0.1 here, so that's 10% of the output sample rate, is usually a reasonable default choice unless you have a good reason to prefer something else. So that's the filter. Any questions about the filter?
I guess a comment and a question for me. I mean, this should be familiar to those of you who have been looking at, filter bank files from GreenBank or the ATA or whatever radio telescope. This filter roll off at the edge of each of the coarse channels. I'm curious, Daniel, do you know what the ATA uses for the skirt?
I don't know what the skirt parameters are, but what I know is the number of taps per filter, which I think it's only 4 or maybe 6. So that's the reason why it's a pretty poor response. Essentially, the problem is that not only the skirt is pretty large, but also the passband is not really flat at all. There is like some ripple like this to it, and there is a good amount of aliasing. Next week, I will actually do a polyphase filter bank, and I think I have somewhere the ATA PFP response, so I might even show how it looks like exactly.
Right. Can you explain a little bit more on how like mathematically you can have a filter that's just kind of a brick wall and cuts everything off?
Yeah, I can give you the mathematical answer. But it's based on complex analysis facts. So I'm going to give you the answer so that you can have an answer. I can definitely answer properly for these filters, but there are other types of filters. So for these filters, they are a finite list of numbers that essentially get convolved with the signal. That's the operation that is going on. And then the frequency response of those filters is essentially going to be what is called a trigonometric polynomial. So that's a polynomial in cosine and sine rather than a polynomial in the independent variables. And that's easy to show. Basically, you have your final list of numbers, work out what is the Fourier transform of that, and out it comes a trigonometric polynomial. And then this is a fact which is well known about polynomials, like regular polynomials, and it's the same for trigonometric polynomials. A polynomial can only have finitely many zeros. You might remember this. So if you want your polynomial to be 0 over a certain interval, or if you want your polynomial to be 1 over a certain interval, essentially, if you want your polynomial to hold a constant value over a certain interval, that forces the polynomial to be constant. The only polynomial which is 0 over an interval is the polynomial which is 0 always. And so essentially, you cannot have a polynomial which is like 1 constantly on an interval and 0 constantly on another interval, which is the brick wall response you are asking about. So that's like the simpler version of the proof, which applies only to these finite impulse response filters. But actually, the same is true for a filter which is causal. That means which it doesn't look at signal from the past or from the future, sorry, which is like cheating. You cannot have a filter which looks at signal from the future because it hasn't happened yet. And then what happens is the kind of function you get for the frequency response is no longer a polynomial because you can have infinitely many coefficients. But it's an analytic function. There are other theorems about analytic functions that say nearly the same, that they cannot be 0 on a whole interval. They can have infinitely many zeros, but they cannot cover a whole interval.
Okay, thank you.
But great question. Yeah, I do not take these statements as just the truth. It's good to ask about what's the reason behind. Any other questions or comments? Okay, so let's move on. The thing we want to do now is we have this red signal, and because of the filter, there's nothing outside this -50 to +50 kilohertz, so we can apply decimation to it. And I'm actually going to do this like so, so that we can have both the result of the filter and the result of the filter plus decimation. And I should call this signal after filtering and decimation. And then I need to set this to another part of the GUI. Usually no one does this because one of the main reasons to apply a low pass filter is to decimate immediately afterwards. There is this decimation field, which we could set to 10, and then that is going to do the effect of these blocks combined. But because I want to show you this intermediate output, I'm going to keep things separately. So if we look at this, we can see a difference between this plot and this plot. First of all, the signal power is the same, nearly the same. -19, -19, -20. I don't know. It's pretty much identical. However, it is quite clear that the noise floor is different. And the reason for this is now we don't have these extra copies of the noise which are being folded on top of the noise floor. So now we have the same signal to noise ratio as in the input signal. This is at -45 thereabouts. This is at -19. And because I'm not decimating by 10 by 8 as before, the FFT size is not this one divided by 10, but it's close to it, and we can run the numbers exactly to see that the signal to noise ratio is maintained. So we are not losing any signal to noise ratio. So that's great. We can also see that the spectrum is no longer flat. So we have these like this roll off at the edges. That's just the effect of the filter. Anytime you see some kind of recording or something like that that has a noise floor which is completely white and flat, it has either been whitened in a very careful way, or it is artificial, like what I'm generating here. Because no kind of filtering, either in the real world, like analog filtering or digital filtering, would leave you a completely flat spectrum. You will always have something near the edges where it needs to drop off. So, okay, let's check now the effects of aliasing. I'm going to do the same experiment as before, just keep increasing by 10 kilohertz, and still this thing is in the passband, so it's doing what it needs to do. 10 kilohertz more, it's still there. Then 300, I'm actually going to do 79 so that we can see it close to the edge. And we can already see something here. So I'm going to point this out because it's interesting. You can see that the filter skirt already begins and the signal is being attenuated by some amount of dBs, maybe, I don't know, 4 dBs or so. It is easier to see that here because we have the input and the output, but we could also compare these with the input signal. So the signal is starting to drop in power as we are getting closer to the edge of our spectrum. 380, we have the same effect as before. Now the signal is like in the two edges of the spectrum. It has been attenuated more. I'm going to do 381 for the sake of the demonstration. So we have some aliasing. And that's important to keep in mind. Having absolutely no aliasing on the edges of the spectrum is impossible and reasonable. It depends on how you want to put it. I will show you how. It essentially involves making this filter narrower and then losing more amount of spectrum. But if you don't want to make the filter narrower, then we are going to have some aliasing on the edges because the filter doesn't drop off immediately. It doesn't have a completely brick wall response. So to show that, I'm going to keep increasing, and now at 382, you can see that it's more attenuated, 383 more attenuated, and in here, because we don't have any filter, the signal is not attenuated at all, and that's a problem. And as I keep going, at some point the signal disappears. We can see it occasionally there. 385. You can see the signal is there, but now because this is mixing with some of the noise that is there, the signal is now below the noise, as you can notice, and we can no longer see it. So maybe 5 kilohertz in here are affected by aliasing, and that's good to know, and that's what happens. But this is the proper way to do decimation. We filter with something like a low-pass filter, and then we decimate. Questions here? Okay, this is just such a common operation. So shifting the signaling frequency by multiplying by local oscillator of the right frequency, then applying a low-pass filter, and then applying decimation is such a common operation that there is a GNU Radio block that does that. And it's called frequency translating FIR filter. There is another one, which is FFT filter. It just implements the filters in a different way using FFT, which is more efficient sometimes, but not always. And I think I showed that last week. So this block is the combination of this one, this one, this one, and this one. And it's actually doing some signal processing tricks to do fewer computations than the sequence of blocks, because you can notice that in this multiply conjugate and in this signal source, we are generating data at 1 megasample per second to then apply a low-pass filter and then to throw away 1 in every 10 samples. Maybe this is a good point to mention that if I use the decimation here, the output I get is equivalent to these two blocks. But what happens under the hood is not the same, because when I have the blocks separated, this block is computing 1 million samples per second, and then this block is throwing is keeping 1 sample in every 10 and throwing the remaining 9. So there's an advantage to setting the decimation here, which is that this block will not compute the samples that do not need to be in the output. It is just silly to compute 10 samples here to only keep 1 of them and discard the remaining 9. So that's the reason also, besides practicity, that there is a decimation parameter in this low-pass filter. So that is one of the signal processing tricks that also go into the frequency translating FIR filter. The second signal processing trick is to actually perform the frequency shift at the end, because if we do that, then the sample rate at the end is lower. So that means we need to generate fewer of these cosine function samples, which is good. We save calculations. We need to do fewer of these multiplications. The pay-we price for putting this at the end is that we cannot use a low-pass filter anymore. We need to use a band-pass filter, which is nearly the same thing, but rather than letting low frequencies pass, it lets a band of frequencies pass. And we need that because if we don't perform this frequency shift at the beginning, then our signal can be at any location in the spectrum. So we need a bandpass filter for that location. But that's just like an interesting side note about this filter is slightly more computationally effective than a sequence of these filters, of these blocks, sorry, not all of them are filters. So you might want to use it. So just as a demonstration, let me show how to set this up. Decimation. Then what do we do about the tabs? I showed that last week, I think. There is a low-pass filter tabs, and we can give it a name. We can set the same parameters. So sample rate divided by decimation, cutoff frequency 0. Sorry, I'm getting ahead of myself. That is the cutoff frequency. The sample rate is just sample rate. And then I had this set to sample rate divided by decimation. So I'm setting the same parameters as here. And then this ID is, this is setting a variable basically with the filter coefficients. And this ID is tabs. And the beauty of doing something like this is that we can actually see the filter as a list of numbers. So we can see there are 241 numbers, and the numbers are there. And for example, if I decrease this, we should get more numbers. So 481 numbers, essentially twice as many numbers. So the filter needs twice as many calculations on the CPU. Okay, so that's it for the tabs. And then the center frequency, we can set it to tune frequency. That plays the same role as the signal source, and you don't need to bother with any multiply conjugate or anything else. Let me connect this right to the input and show that this is giving the same output. So maybe the easiest way to show it is by adding a second input here. So we can see that they are very much identical, slightly different here at the edges because, well, the way this bandpass filter is built is maybe not exactly the same as the low pass filter. Maybe there is like some numerical precision differences or some small amount of rounding, whatever. But in the rest of the spectrum, the two signals are so close that it's almost impossible to see the difference. So that's this is the normal way of doing filtering and decimation in GNU Radio. Just as another side note, if you're doing this very quickly and you know the syntax, it's also possible to call this low pass filter generator directly here. It's basically you call this filters, which means filter description, low pass, and then you put all the parameters which are in here. Those are the parameters to the function because this is just a function we can call from Python. So sample rate divided by decimation and then 0.1 multiplied by sample rate divided by decimation. And you can see that this gives me 241, the same list of numbers. So I normally write this because it saves me from putting another block in the flow graph. But for simplicity, you can use the two block approach. This is also good if you want to have like multiple filters with the same settings, because then you have one of these and you use the same tabs on multiple filters. And if you ever want to change something, you change it in one place. Okay, questions here? So that's what I had regarding filtering. We will take a 5-minute break. So that's until, I don't know, 9 minutes past the hour, and then resume with an FM receiver. And if you have your RTL SDR sticks, you can use those to tune to real FM stations. If you don't, there is a recording here that you can click and it will download, and hopefully it takes less than 5 minutes to download. So you can have the recording and use it instead of the RTL SDR stick if you don't have it. Okay, let's take a break. So I have gone ahead and opened the flow graph, which is in here in FM broadcast. This is essentially ready to go, and you can select either between this RTL SDR source or this file source essentially by disabling one of them, right-click disable, and enabling the other one. So if you have downloaded the file which is linked here, so this file, and you point this file source to the path of the file, it might be in a different place in your computer, then that should be ready to go. If you click play, it should work. There might be some adjustment to do here on the audio sync. This is the thing which is sending the audio to the speakers. Usually, if you don't put in a device name, it will pick whatever sound card or sound device it makes more sense to use. But in some computers, there there can be issues and you need to specify something manually there. So that's maybe the only thing that could go wrong if you try to run this. If you try to run with the RTL-SDR source, then one of the things you need to do is to select a frequency of an FM station, which is in your location and which has a decent signal. Here I've done so for my location. So I'm setting this thing at 98.5 megahertz because I know that at 98.8 megahertz, there's a good station that plays classical music and it's pretty strong. So I'm tuning to that station by putting the center frequency to 98.5 on the SDR and then tuning to 300 kilohertz using this frequency translating FIR filter. And we will see that in a second. So you will need to adjust these two for your local FM station if you are trying to run these now. So the flow graph is pretty large, as you can see. I'm going to use it as is because there is no way I can build this and explain how it works in 15 minutes. But I'm going to explain it step by step. So I'm going to begin by disabling most of it, or actually maybe all of it will be simpler. And then I'm going to keep explaining it by sections and enabling things as we go. And so the first thing is what happens if I have my RTL-SDR source and just connect it to a good degree frequency sync. This might be the thing you need to do if you are about to search FM stations in your location. By the way, just something to keep in mind, if we are using a file source, we don't need any throttle block if we have the audio sync, because the audio sync will set the rate for us. Essentially, we are setting sample rate 48 kilohertz. So that will set the rate at which everything is running. But until we get to enable this audio sync, it will be necessary to include a throttle block here. Otherwise, this will just play in a loop very, very fast, and it will be difficult to see things. So, okay, at the beginning, nothing too strange. RTL-SDR, basically same settings than in other tutorials, and this is the FM station we want to tune to. So you can see it's at 300 kilohertz, as I said before. And then also the bandwidth of one of these FM stations. So you can note the typical bandwidth is like this. I don't know, it's about 200 kilohertz, something like that. So then the first step is we basically want this single station, we want to single it out. There are other stations we are not interested in. So what to do, just the same thing we have learned in the previous half of today. Use a frequency translating FIR filter to remove or actually to crop out just a single part of the spectrum and remove everything else. So this is what I have here, and you can see it's essentially what we have learned. I'm decimating by 10 because my initial sample rate is 3.2 megahertz or megasample per second. This will leave me 320 kilosamples per second or 320 kilohertz of spectrum, which is just the bandwidth of the FM station plus some margin. Taps, basically the same formulas as before, nothing new. Center frequency, there is this tune frequency, sample rate. So nothing new right here. You can see this is just like a direct application of what we have learned before. And you can see this station is now neatly centered at pretty much 0 kilohertz and occupying maybe, I don't know, 80% or 90% of the spectrum at the output here, which is from minus a 60 kilohertz to plus a 60 kilohertz. And we have another FM station here. We could make the filter slightly narrower if we want to. Because this is weak, it doesn't matter too much. We can leave it. In the United States, you have high definition radio carriers. So these are like square blocks here and there. You might want to play with the with the cutoff frequency of the filter. So maybe, I don't know, making it like 0.4 to get rid of those signals, because if you don't get rid of those signals, they will interfere with what we are going to do next. So you can see what's the effect of having a narrower filter. Essentially, we cut earlier, and now we can see the skirts of the filter in the output. You can adjust these depending on your RF environment, if there are other signals, etc., etc. So, okay, this signal is frequency modulated. That means that to encode the information that we want to transmit, we change the frequency of the signal in real time. And you can imagine how that works. For example, my voice is a waveform. I could want to broadcast that using frequency modulation, and if I have this waveform, it's going to be waves, right? It's going to be positive, and sometimes it's going to be negative. And sometimes I was showing something like this on the first tutorial, and we will see something like that also in this tutorial. So we take that function of time that is sometimes positive, sometimes negative, and we use the value of that function to shift the carrier frequency. So these 98.8 megahertz slightly in frequency. We shift it up to encode positive part of the wave. We shift it down to encode the negative part of the wave. And one question is how much we shift it. So for something which has amplitude +1, for broadcast FM, we actually shifted 75 kilohertz. That's known as the deviation. And that is somewhere in the broadcast FM standard. So people have agreed on what's a reasonable setting for the deviation, and that's 75 kilohertz. So I have that set here. And then I have this quadrature demodulator block, which I will explain in more detail in a second. But this is one of the ways of receiving frequency modulation in GNU Radio. It's one of the ways of measuring the frequency of a signal, because the way to demodulate this frequency modulation, or to receive the information which is encoded in frequency modulation, is just to measure the frequency. So how much has this thing been shifted in frequency at any point in time? So we use this quadrature demodulator block. This has documentation. There's a formula here in LaTeX. I think it's slightly better in the wiki. It's actually pretty good. There's even a picture. People keep updating this, so it gets better and better every time. The frequency of a signal, as this formula says, is basically the instantaneous change in phase of the signal. That's the physical definition. It's the time derivative of phase. One way to approximate this time derivative is by taking the difference of two consecutive samples and dividing by the sample period. That is a very simple way to approximate the derivative of a quantity. Probably you have done that many times in your life. For example, in NumPy, there is this NumPy diff formula. If you give it an array, it will compute the difference of adjacent elements. And that's a reasonably good approximation for the derivative of that time series. So here it's the same. We are approximating the derivative by subtracting phase and dividing by the sample period. However, because if you notice, this block doesn't have the sample rate, it doesn't know the sample period. It only has a gain, which is by how much we multiply the output. So the only thing it's actually doing is this phi2 minus phi1. It's only computing the phase difference of adjacent samples. If we want to scale that properly, then we need to divide by whatever quantity is the sample period, maybe adjust units, because usually these phases are in radians, but we express frequency in hertz. So we need to divide by 2 pi to convert radians into cycles. So that's probably explained somewhere here, like there is a phase divided by 2 pi. So that's basically this thing. If we want to divide by the sample period is the inverse of the sampling frequency. So we need to multiply by sample frequency. And then if we want to convert from radians to hertz for the frequency, we need to divide by 2 pi. So that's the gain we would apply. And then this is speaking about FM, it's speaking about deviation. It says that when we have a frequency modulated signal, we want to normalize. For example, if we see that the frequency is 75 kilohertz, that matches our deviation. We want to see a 1 at the output. So we divide also by deviation. In that way, if the deviation is maximum, so if the shift of the signal reaches plus 75 kilohertz, we will see a plus 1 in the output, and so on and so forth. So that's the explanation. You can read the full text if you want. And that's the formula I have. Basically, I have sample rate, but I also have this decimation here. Let me try to make this larger. Do I remember how to make this larger? Maybe, yeah. So basically, sample rate divided by decimation is the sample rate I'm dealing with in this block. And then I have 2 pi deviation. So essentially, I'm using the same formula, which is here. And there is all the explanation and all this mathematical description, which is maybe too detailed for my taste. But you know, this is a wiki for all sorts of people, so it's good that it's here. So this is how we extract the frequency information of the signal. Now, the next thing I have is this spectrum display. And I'm going to set it to 1 input so that we can look at this. So this is the spectrum after quadrature demodulation. And we can see a bunch of signals. Maybe I'm going to zoom in. First of all, because here we are measuring the frequency, this is a real quantity. We are no longer operating with complex numbers. So then the spectrum is going to have only positive frequencies. I have set this to half. We have spoken about this in the past. We can see something here, we can see something here, something here, something here. So what's all of this? This is actually the main signal of the FM station. The other ones are auxiliary signals, which are modulated on top of it. This is the voice channel or music channel or whatever it is. It's the audio channel, but it's actually a mono channel. So just one single channel of audio. We are going to use that. We are going to see how to convert this into audio we can listen to, and then I will go back to the other 3 signals. But you can already start suspecting that maybe stereo has to do something with it. Like people maybe want stereo radios, and how to do that, because stereo is left and right. So we have 2 signals, and then there is the question, I have 2 audio signals, how to put 2 signals together in the same radio frequency wave. So we will get back to that. But for the time being, let's focus on this one, which is the signal that is the mono part of the station. This one is very simple to interpret. It's just the raw audio. So you might remember that human hearing range goes from quite low frequencies, somewhere about, I don't know, 20, 30 hertz, to, depending on your age, 10 to 20 kilohertz. So that is what we have here. Basically, we have frequencies from almost 0 up to, I don't know, maybe 15 kilohertz, which is like high quality audio. So all of this is included here, and that is the mono audio of the station. What to do? Very simple. Just we have the audio here. We need to apply a low pass filter to remove all the other signals, and then send it to our speakers. So, well, maybe questions before doing that.
So if those other signals are beyond the range of human hearing, why do you need to discard them before sending it to the speaker?
Well, that's a good question. So this one is 19 kilohertz. It's barely beyond the range of human hearing. Young people can actually hear 19 kilohertz. Also, not a good idea to send ultrasound to your speakers. So the sample rate we are going to use with the sound card is 48 kilohertz, and we might even want to use a higher sample rate. So that actually lets everything up to 24 kilohertz pass. So that will definitely pass to the speakers. Not great. And the other ones, yeah, good point. They are removed anyway, but I prefer to do it like orderly. So let's extract the audio signal and then let's send it to the speakers. It's just a matter of keeping things tidy. But yeah, these we don't have a way of sending them to the speakers at 48 kilohertz sample rate. Other questions? Okay, so let's do that. We have a low pass filter. And then basically we are following what I have remarked. There is a tone at 19 kilohertz that we want to remove. I will get back to why there is such a tone. But for the time being, we just want to get rid of it. We have seen that there is frequency content in the audio up to about 15 kilohertz. So 17 kilohertz is a reasonable place where to put our cutoff frequency. That's what we do, and transition width 1 kilohertz, why not? So this is isolating the audio from the other signals. And I had a second input here for me to be able to show this. So you can see the effects of this filter. It is just as you might have imagined. It is cutting off here at 17 kilohertz. It's removing this tone. Now it's extremely weak. It's removing everything else. And the audio signal remains. So now we need to do basically a single thing to send this to the speakers. We have a sample rate of 320 kilohertz. Sound cards usually do not work at that sample rate. They support a few different sample rates. One of them, probably the most popular, is 48 kilohertz. So we need to adjust our sample rate from 320 kilohertz to 48 kilohertz, which also implies some filtering because it's a decimation by, I don't know how much, for 320 divided by 48, 6.666. That's good because it actually makes my case for using this block. So far, we have learned how to filter when we want to apply a decimation by an integer factor, be it 10, as in the example before, 17 or 1003. But we don't know how to decimate by 6.6666. There are ways. One of them is with this rational resampler, which does something smart that I don't want to spend time describing now. To interpolate by 48, because that's what I'm putting here, and decimate by 320. And so the net effect is to decimate by 6.666, because that's the quotient, without computing all the intermediate numbers that we would throw away anyway. And if we set the tabs as this empty list, the tabs will be auto-calculated as an appropriate anti-aliasing low-pass filter for the output. And the fractional bandwidth as well. 0 doesn't mean 0 fractional bandwidth. That doesn't make sense, means auto-compute. So this is a quick and simple way to convert from 320 to 48. I'm going to leave this FMD emphasis block aside. I will come back to it, but I'm going to skip it for the time being. And what I'm going to do is I'm going to connect this and enable this one and this one. I have this multiply constant block as a volume adjustment, and I have it set at 0 because I don't want the station playing over my voice all the time. This is controlled by an audio gain, and hopefully I have my audio sharing over Zoom working today. We will see. It's not a huge deal if it doesn't work. but we will see. So I'm controlling that with a QTQ entry, which is here, audio gain. And then I'm showing the audio signal mono in a time sync, and I'm sending it to the audio sync, which is the speaker. Let's see how this works. So we can see the waveform of the sound. This is set to, I think, 1024 points, which gives us about 20 milliseconds or so. So you can really see like the waves and even estimate what frequency this is from just looking at this plot sign. You can see how it's changing all the time. So let's see if my audio sharing is working. Does it work? I hear a person speaking in Spanish.
Yeah, we're not hearing it. We don't hear it.
Okay, I think I can do something really quickly to try to get this across. Let me try.
Opiniones nuevas también y centrarnos y poner al día al propio Wagner.
Pues un honor por nuestra.
Yeah, we got it.
Okay, excellent. So I basically need to switch between computer audio and microphone, but that's doable. So you can hear a person talking about Wagner's music or whatever that was. So excellent. We have our thing working. Maybe some of you have been playing on your computer and have this working for a local FM station. What to do next? So this is just a mono signal. It is one audio channel, but we know that there is stereo left and right. Many broadcast FM stations, not all of them, but many support stereo. And the question is, how does that work? And the answer is in Wikipedia and in many other places. So I'm going to show you the formula in Wikipedia. And that's shown here. So what happens is A and B are left and right. These A and B are the left and right channels. We form a mono signal, which is the mean of the two, the average of the two. It makes sense. If you are going to have a mono signal from left and right, you cannot do any better than just the average. And then we have a different signal. So something which is very important is that we can recover A and B from their sum and difference. That's a very simple calculation you can do. But then the question is, okay, if we have the mono signal and we have the difference signal, how do we send these two signals over the same FM modulated thing? And the answer is we cannot send them right on top of each other. So that would be equivalent to putting both of them here because they would interfere with one another. So the only dimension that we have to play with is frequency. And then the only idea that comes to mind is if we need to send two signals, we can shift the other one and put it at a different frequency. So here at 38 kilohertz center frequency is the left minus right signal. And previously we couldn't see anything because I don't know, there was like a silence in the program, but now you can see there is some audio going on here. So that is because there is perhaps some music, and music usually has like a good stereo as opposed to people talking over a radio program, which often doesn't have such much stereo content, but music does. So that's another reason why I'm using this station for this demo. So we can see it comes and goes, but this is the left minus right signal. We can recognize this in the formula because there is a pilot tone at 19 kilohertz, which is an auxiliary signal here, which is just a CW carry. This is a 19 kilohertz signal, which is not modulated. And it's only used as a means for the receiver to recover the center frequency of this thing. I will get back to what that means exactly in a second. But for now, we have this FP, which is 19 kilohertz. We have this 19 kilohertz sinusoid. It's multiplied by 0.1 because it's supposed to have less power than the other signals. It's only an auxiliary signal for the receiver. And now we have twice the frequency. So this is 2FP multiplied by the sine of 2 pi. So this is a 38 kilohertz tone. We are using this to shift the second audio signal, so the left minus right, in frequency. Note that we are multiplying by a real sinusoid function. This is not a complex exponential. And the reason for this is it wouldn't make sense to put a complex exponential in here because that would give us complex numbers. And this is supposed to represent a frequency shift. So it needs to be a real number. So we have this real sinusoid. And then the effect of a real sinusoid, we have learned that in one of the previous tutorials. It's actually making the signal appear as two mirrored copies in the spectrum. It is not easy to see at the moment because it is somewhat quiet, but maybe you can see it. So there are two copies basically of the same information. These are the positive frequencies of the signal. They have been shifted above 38 kilohertz. So this would be the 0. And then this is the mirror symmetry, if you want, of the same. It is the same information. This is just caused because we have this real subcarrier. This is called a subcarrier because it's a carrier that is used within the main radio frequency carrier to encode any other additional information. So that's the structure of the stereo signal. And then the question is, why do we actually have this pilot tone at 19 kilohertz? Well, the reason is the receiver actually needs to be able to recover the center of the 38 kilohertz very accurately, because if it's tuned with some small error, we would see that as a pitch difference in the audio, and it would be horrible. So the way to make the receiver essentially perfect when determining what the center frequency of this is to give it a clue, to give it a tone which is generated on the transmitter that is at half of the frequency at the center of this, and then the receiver is going to take this tone, multiply the frequency by 2, and then arrive exactly at the center. Because this tone was generated at the transmitter and it's not something that the receiver is generating locally, it will always be consistent with the place in which the transmitter has put this stereo signal that now we can see clearly, quite clearly, and we can see that it's symmetric. So that's the reason why we have this pilot tone. It is fairly common to have pilot tones both in analog transmissions and in digital transmissions. In digital transmissions, they look somewhat differently. They might not be unmodulated like a pure sine wave. They could have some pattern which is known to the receiver. But that's the idea, to give something to the receiver that helps the receiver do its job properly. Next, I'm going to show you how to do this thing I've described in words, which is to take the frequency of this thing, multiply it by 2, and use that to recover the center frequency, and then use that to mix this thing to baseband. That is the thing we want to do, to shift this from 38 kilohertz to 0, so that we can recover the audio here. Before showing you how to do that in GNU Radio, any questions? Okay, let's get to it. So maybe something else, because I see I have left this FM de-emphasis block. I'm not going to do a full demonstration about this block. You can play with it and compare on your own what happens if you leave it out of the way, like here, or versus what happens if you include it, as I'm going to do right now. The reason we have this is because the effect that noise has on a frequency modulated signal is higher at higher frequencies. So if we don't do anything, then that means that when we listen to the signal, there is like a high frequency hissing noise, unless the signal quality is very, very good. You might have even hear that when I played the FM station. So the trick that people agreed on doing is pre-emphasis and de-emphasis. That means before transmitting, we are going to multiply high frequencies to make them larger in amplitude. And then on the receiver, we are going to do the inverse transformation. We are going to make higher frequencies smaller. And then by making high frequencies smaller, we make this noise smaller. Essentially, we are whitening the noise by, on the transmitter, applying the same frequency response that we know the noise will have from the point of view of the receiver. So that is what's called emphasis. On the receiver, to do things properly, we need to apply the emphasis. It's implemented by this block. It's a filter. It actually comes from a very simple analog filter, which is implemented with a resistor and capacitor. And here you have formulas and everything. So it's not a very important filter in digital signal processing, essentially because it comes from electrical analog circuits, and there are different and better ways to do things in the digital domain. Something you need to keep in mind is that there is a time constant in the filter, and it's slightly different in the United States and in Europe. I have this set for Europe because that's where I am and where the example recording and the station I'm showing are. For the United States, to be 100% correct, you need to set this to 75 microseconds. But it's probably difficult to be able to hear the difference. Okay. So that's what the de-emphasis block is about. Then let's get on working with the reference tone at 19 kilohertz. First of all, we convert it to complex. That's as easy to do as adding an imaginary part, which is 0. Then the next thing is we need to recover the frequency of this tone, because the tone might be noisy, there might be other signals around it. So there is a block which is called PLL carrier regeneration. Because I only have 15 minutes left, I don't want to go into details of what a PLL is. The only thing you need to know about it is that it is a signal processing mechanism that locks to the phase of a signal. PLL means phase lock loop, and it will track it. So in this case, we lock to the phase of this 19 kilohertz reference tone, essentially to track the frequency. In this way, we recover the tone with no noise. So carrier regeneration means make a clean replica of this 19 kilohertz tone, which has the same frequency, has the same phase, and has amplitude 1 constant. So that's how the receiver generates a local clean 19 kilohertz tone, which is locked to the transmitter tone. So that's what we do here. And then the other thing we need to do with the stereo signal is we convert it to complex. And then we multiply. So there are two multiplications. First of all, there is this 19 kilohertz tone, but I want to have a 38 kilohertz tone, because remember, the center frequency for this is this 38 kilohertz, twice the pilot frequency. So the way to compute something which is twice the frequency is to compute the power 2, basically to multiply it by itself. Way to understand it, I'm shifting 90 kilohertz with 19 kilohertz. So I arrive to 38 kilohertz. And then multiply conjugate. In this way, I'm shifting my signal. This FMD mode is the output of the quadrature demodulator. So right here. So I'm shifting it to the left by 38 kilohertz. And then, but very important, these 38 kilohertz are generated from the reference tone. These are not a 38 kilohertz signal source that I would put in here, because that wouldn't be fully synchronized to the transmitter signal. Then, just for visualization purposes, I want to show you what happens with the signal. So I'm going to plot the real part and the imaginary part separately in the spectrum. So where is this plot? It's actually here. And this might not be completely easy to see, because there is like other noise, and It also depends on how good my recovery of this carrier is. But supposedly, this stereo signal needs to appear only in the red part, which is the imaginary part of the signal, only in the quadrature component, because it's multiplying the sine function, essentially. You could also have cosine of the same multiplied by something else. But this thing is going to appear in the imaginary part when we shift things. You can do the math to figure that out. So not completely clear in this plot. Maybe I'm going to try to raise my antenna the same. In other cases, it's clear. Maybe, I don't know, maybe I need to tweak my frequency recovery thing once again. But you can believe me on this one. So we expect our audio signal to be in the imaginary part because of how the math works out. So we can do the same. Low pass filter, 78 kilohertz cutoff frequency, rational resampler. Now we have it at 48 kilohertz. And this is the stereo signal, which is the difference between left and right. So let's enable a bunch of things here. Mono audio, where was that? Here. Let's show the mono and stereo signals. Let's also recover the left and right. So if this is the sum and this is the difference, if I sum them, I get the left channel. If I subtract them, I get the right channel. And the emphasis is supposed to be done separately on the left and right channel. So that's the proper way to do the emphasis on stereo audio. So this is my signal. I need to disable the audio sync here because I don't want to have two different audio syncs. And now we can see the audio signals. So you can see the left minus right signal. It depends on what's being played. Sometimes it's very quiet because it's almost the same content in both left and right. But you can see also left and right in green and black. And you can see they are always slightly different because of this contribution of left minus right. And depending on the music, we might see a higher amount of stereo content or a lower amount of stereo content. I'm going to switch over to the audio here so that you can listen. Okay, so that was some opera. That was supposed to be in stereo. I'm listening to it with headphones, and I can barely notice that it's stereo. You can also look at it on the left and right. I can see that it's stereo with my eyes. Other kinds of music, depending on how they are recorded, have more stereo content. So you can run experiments on your own. Questions so far? Okay, so the only thing we are left with for the remaining 10 minutes of today is what is this thing? Anyway, this is at 56 kilohertz, I guess, which is 3 times the pilot frequency tone. It's not a coincidence that it's at 3 times. It's if you want to send another signal, which is not the stereo audio, where do you put it? You put it at 3 times, and then the receiver can use the 3 times the carrier to use this information. So what could this signal here be? What do you think it is? Okay. Any guesses? You might have noticed that in some radios, for example, in car radios, there is a small display that says the name of the station that is being tuned to, even the name of the song that is being played, essentially some information in the form of text about what's going on in the station. And you might have wondered how that works. It's not magic. It's not getting the data from the internet because this needs to work without any internet access. So of course, it needs to be something which is included on the FM signal itself. And since we are speaking about the name of the station, also the name of the song, we are speaking about text. We are speaking about data. It's not sound anymore. So the best way to encode that is digitally with ones and zeros. We can encode text using an alphabet and digital messages. So that's what's here. It's called RDS. What does it stand for? Radio Data System. I have the Wikipedia page here so that I don't forget. So Radio Data System, it's a digital signal that can be sent alongside FM radio stations to show some basic information about the program contents. So that's what RDS is about, digital communication signal. A very simple example, but it's a good example. And I'm going to show you next how to process that with GNU Radio. Up to some point, we are not going to decode the text and everything. We will just see like ones and zeros. From then on, it's relatively simple to pick some tables about what are the fields, what does each bit mean, etc., and work your way through. And the reason I'm showing this is because it's interesting, but also because it ties to something we saw at the Allen Telescope Array. Joel did a demo of receiving images from the GOES satellite with a laptop and an antenna and an RTL SDR. So there he was receiving a digital signal from a satellite that was transmitting digital information in the form of images. And he was showing some displays on the computer besides the images. And because this is an application that someone made, it's like magic. You point your antenna, you have images, but there are things going on in the middle. And I wanted to give you an example of what those things are, not with the GOES signal, but with this signal, which is simpler, and we have it everywhere where there is an FM station. So yeah, that you have a basic understanding about how digital communications work. So let's get to it. The first step you might have guessed is multiply this tone by 3 and shift this down to baseband. So I have RDS, and that's what I'm going to do. I have my FM demodulated signal. I have my reference tone. I'm multiplying it by itself 3 times to increase the frequency by 3. And then I do multiply conjugate, and then I have a low pass filter. I'm running quickly, but the bandwidth of this has been adjusted to be slightly larger than the bandwidth of this RDS signal. And we can see this is the RDS spectrum. Maybe I need to zoom in like this for us to be able to see it, but there is our digital signal. It's not very strong. Maybe if I place my antenna, I don't know. I'm in a not so good location to do this, but nevertheless, it works. So this is the digital waveform. Just to give you a quick idea, this is transmitting ones and zeros. And the way that ones and zeros are being transmitted, you can see this is the spectrum of the signal. It's not in a dB scale, but it's pretty much what we saw. There are 2 lobes. So how are ones and zeros sent? They're sent with something which is called symbols that you can think of as pulses, and the drawing is here. So if we want to send a 1, we go like this, like positive, and then negative. If we want to send a 0, we do the opposite. Basically, we put a minus sign, we go negative, and then we go positive. And that's a single symbol, so that would be like a 1. If we want to send another 1, then here we come and do the same. We go up, we go down, etc. When this thing is multiplied by the 56 kilohertz tone, what remains is something like this. And this wavy thing would be the 57, sorry. I don't know how to multiply, but clearly 19 times 3 is 57. So this wavy thing in between would be the 57 kilohertz carrier that we are going to remove as the first step. So, okay, we have these pulses as symbols. They are encoding ones and minus ones. And in this particular modulation, we go up and then go down. Other modulations, they only go up, and that would be a 1. And then you would do another 1 or something like that. It depends on what you want to do. For example, the spectrum has like a 0 in the middle because of this symmetry. That's the reason to do it like that. So what we want to do is we always want to recover all the power in these symbols. So we essentially have some filter which has something to do with the symbol shape. And what we are doing here is multiplying by +1s on this half and by -1s on this other half to basically to make everything positive so that we can sum everything. That's the thing which is done in this decimating FIR filter, which is another kind of filter. Then we have an AGC, that is automatic gain control. So you have seen that the amplitude of this is 1. Of course, that's 1 in the transmitter, in an ideal world, or in the mathematical definition. In the real world, because signals are attenuated, nothing is perfect, the amplitude of this thing might be whatever. So we need something which is looking at what's the amplitude of the input and then adjusting the amplitude of the output based on some normalization we want to achieve. So that's what the AGC does. And then symbol sync is actually going to find where the symbols begin and end, because we need to align ourselves to these symbols. In the analog station, so the FM station, when we listen to the audio, it's just transmitting a stream of audio, and it's an analog signal. It doesn't have any parts in the signal. It's just a continuous stream of sound. However, when we send digital information, there are always symbols. It's like this is one character, which is 0 or 1. This is another character. Sorry, this whole thing is a character. Then the next is another character. So we need some kind of signal processing algorithm that is able to say, okay, these are the boundaries between characters. So not going into the detail of how this algorithm works, but it is there. There's a block, symbol synchronization. And then finally, because there might be a residual phase offset in the signal. For example, when I was trying to show that the left minus right was completely on this imaginary part, and we were seeing that there was some other signal component in the real part as well. That's the kind of thing we want to get rid of with this block. It's essentially removing the remaining phase and frequency offset the signal could have. And then the result that this is going to give me is a constellation, which we will see how that looks like in a second. I think Joel showed the constellation. And this isn't working properly with the RTL-SDR stick. I don't know why. I'm going to switch to the recording, which I know that works. Maybe, I don't know, I have too much interference or something. So let's use the recording instead of this thing. I will troubleshoot what's going on wrong with the real station. It was working on a couple of days ago when I did it. So you can see when the thing works, there's like a hiccup at the beginning and the end of the recording, because the recording is just a few seconds long. That's the hiccup. But when the thing works, we get two distinct points, one at -1, the other one as 1. These are the bits that are being sent by the station. So they are in the complex plane, but everything which is here is +1. Everything which is there is -1. And then finally, not much. The information is in the real part, as we have seen from the constellation plot. I don't remember if Joel showed the constellation for the GHOST satellite. He might have, he might not have. And finally, another technical detail, because this cost-up loop cannot distinguish, let me show this again. It cannot tell if this is correct or if this is flipped by 180 degrees. So essentially, if +1 and -1 have been interchanged, because if I show you this picture, you don't know if I have rotated it by 180 degrees because of the symmetry. So the Costas loop doesn't know either. And then there's something called differential encoding to fix that, which means if we want to transmit a 1, we transmit it as changing from whatever we had transmit to the next symbol. So for example, we go from a 0 to 1, or we go from 1 to 0. If we want to send a 0, we keep the same value. So we go from a 0 to a 0, we go from a 1 to a 1. And you can do some doodles on a paper to convince yourself that even if you rotate everything by 190 degrees, the information is not destroyed by if we use this differential decoding, because a transition still is a transition even if we rotate everything, and staying with the same value is still staying with the same value even if we rotate. So that's what it is. And then there's this raster plot which basically shows the bits. Because of the way the transmitter works, they are organized in different blocks of I forgot how many bits. It's probably somewhere here, 104 bits. So they are organized in blocks of 104 bits, and you can see the blocks here. This glitch is because of the recording. Look back to the beginning, but I'm going to stop it to pay attention to a couple things. So you can see that in the blocks, there are some pieces which are the same. This is the program ID, which is always the same, and some pieces which are changing. This is because it's different information, and you might notice here, this looks like some kind of pattern. So it's actually because depending on the value here, the information here is different. So this is like information type number 1. There you have the information type number 2. There you have the other information. And of course, there is a manual. There is a reason I have this open. So you can see there is the program information. There is everything. There is like these types of codes, which is the type 1. There's something else. And so you read all of these and you can understand this. Why is this relevant for SETI? Well, if at any point we get something like this from an extraterrestrial intelligence, I mean a digital communication trying to convey some information to us, there is no manual. We will have to go through something like this, like bit by bit. What do I think that this means, to try to understand it based on maybe a common understanding of mathematics and science. And there are people working on this, working on also how to send messages and how to interpret messages if we ever receive them. So you can try to play with this with the manual to see if you can find any patterns in here. And I think it's relevant if we ever find something from NET to be able to, have some tools for where are the patterns here. Maybe I can already see some patterns. Okay, that's the end of today.